Hi, everyone. Thank you so much for coming out. I am so excited. We have a super talk planned for you today. It's about reinforcement learning for autonomous cyber defense. And we have Andrew Lone. He's a senior fellow at the Cyber AI Project, the Center for Security and Emerging Technology. And we also have Crystal Jackson, who's a junior AI fellow, and also from the Cyber AI Project, Center for Security and Emerging Technology. Let's give them a warm welcome.
Thanks all. So we can start with this disclaimer, and you've all seen it before. But moving right along, last year at 4 a.m. Kiev time on February 24th, Vladimir Putin started his special military operations speech. And that speech went for about half an hour. At the end of that half hour, airstrikes were already coming down in Kiev, Dnipro, and Kharkiv, and ground troops started their long slog from Belarus towards the capital. But that wasn't really the start of the special military operation. The day before, just before close of business day, well, precisely 7 minutes and 11 seconds before the end of the close of business day on February 23rd, new strains of wiper malware showed up across Ukraine. They were detected almost immediately. Within an hour and a half, ESET had posted to Twitter with a description of how the thing works and indicators of compromise. Within an hour and a half of that, it already had a cute hermetic wiper. And this was all really impressive speed and coordination. It's exemplary. It's an example of cooperation between corporations and government to create these defensive actions. But was any of that really fast enough for the victims in Ukraine? Now, I presume some of you out there actually know the answer to that. We can only try to piece together what's out in the open source. What we know is that in the first week, there were 22 destructive incidents due to malware like this, wiper malware like this. In the second week, there were 0. So it seems like it did have a really pronounced effect, but maybe not for the primary targets that were already hit. Over the last few or many years, AI has really done a great job in detecting malware, detecting anomalous or malicious behaviors, but that's really just a fraction of what defense does. We'd like to talk today about automating other parts of that. Before I get into the details, we'll lay out where we're going with this. We're going to talk about reinforcement learning for autonomous defense. Reinforcement learning is not the only approach to creating autonomous agents, but it's one promising one. That's what we'll focus on today. We'll talk about why reinforcement learning, or just how reinforcement learning wasn't a very promising or pursued approach for this for many years, but also how that's changed recently. We'll talk about some of why that's changed and some of the tools and techniques that are available. We'll show you how to use those tools a little bit. Then we'll talk about how much room there is to grow, where the walls might be, how much this can scale out, before leaving with you some ideas about how you can take this back to your own organizations. Backwards? Okay, so like I said, detection is just one small fraction of what defenders do. Laid out here in the NIST framework, that becomes particularly clear. We can see that maybe starting in identification, it's a pretty human-intensive activity. I should note that all of these have AI in them, but human identifiers need to do things like threat intelligence or determining the vulnerabilities of their networks. At the protect stage, it's the same sort of thing. Human defenders might need to adjust the configurations on their endpoints or in their network, and they may need to figure out how all the ways that they need to harden their networks. Response and recovery is kind of the same. You might need to determine which processes to kill, which pieces of or which endpoints to wipe, or which services even to shut down in some cases. What we're talking about today are autonomous agents that can do all of these types of things without direct human tasking. And that's a pretty ambitious request because we don't really even give human defenders enough autonomy to do a lot of these things. You can imagine if a human defender needs to wipe or to kill a process or wipe an endpoint, they might need to discuss with that endpoint's users before they could do something like that. Or if they're going to do something that takes down a service, they might need approval all the way up to upper management before they can do something like that. Now that's debilitatingly slow for human defenders, but it's kind of a non-starter if we're trying to operate at machine speeds with autonomous agents. And so we worked with our colleagues at Turing Institute in the UK, Anna Knack and Ant Burke, and they interviewed a couple dozen researchers and practitioners in this space. And you can imagine that everyone has their own definition or vision for what autonomous cyber agents are. Those differences of opinion have kind of been boiled down into these 4 categories I'll talk briefly about here. The first one is, what should these agents be able to do? What are the actions that they should be able to take on? And some can't imagine any agent being able to do anything that might break a service level agreement, for example. That's too much to expect. Others envision that these agents could do anything that humans can do, and sometimes even more. But aside from the individual actions that they do, there's also disagreement about how much range of action any agent should be allowed to perform. Some envision a single agent that can observe entire networks and endpoints and take all of the defensive actions that are available. And others think that's too ambitious for a single agent. They envision a bunch of smaller agents that can each observe smaller fractions and take a smaller subset of actions and can maybe communicate with each other to, as a whole, create a cohesive autonomous agent. Now, the operational boundaries of where these things should be contained is another area of disagreement, or of varying definitions. Some envision that these agents should only be on the endpoints or networks that are being defended, or perhaps spread across a large array of networks. Like you can imagine an organization like CISA deploying these things across a vast set of networks, or even like a Cloud Defender might have a vast set of networks. Some envision going beyond that one level to similar networks, that these agents should be allowed to traverse outside of where they're defending to try to gather more threat intelligence, maybe moving into gray space. Some imagine moving all the way into red space for even more threat intelligence, and some even imagine taking offensive actions in those red spaces, but we certainly stop short of that. It seems too escalatory for us. Now, I mentioned already a little bit about the degrees of autonomy that people might vary in opinions over. You can imagine that, again, breaking service level agreements might be a thing that's necessary for a defender at times, but you wouldn't want to give that autonomy to a machine, or maybe you would, but let's say that you don't. Where does that leave you? Some can envision these agents being able to anticipate several moves into the future and say, maybe if I follow this path, if the defender takes this action and I have to respond, that leads us to this place 3 moves into the future where we might have to take the service down temporarily. Now, if they can anticipate that, they could request that approval. That might be able to give you time. That's too fast for many. But you can also, it's important to keep in mind that machine speed does not mean instantaneous. We've all impatiently waited for a large file transfer or maybe an encryption of something or code compilation. You can also imagine that if one of these agents spots some sort of suspicious file transfer, they could throttle that, slow it down to try to buy more time for the humans to be involved here. Also, attacks don't always move at the fastest possible rate. They might try to be slow on purpose to limit detection. And so machine speed doesn't necessarily mean instantaneous. That can also give the opportunity for humans to be involved at various levels. If we're able to go slow, maybe humans can be fast enough to be in or on the loop, managing decisions in real time. Many of us think that that's not fully realistic here, that these agents will be too fast for that, and that humans will be some sort of manager setting thresholds maybe for how aggressive to be, or just giving feedback, like your performance was too aggressive in this case, let's dial it back down. But one other aspect is important here, that it's not just the speed that could be a problem. These autonomous agents might be able to take actions or run strategies that the humans don't even understand. At times, this has been the case in other reinforcement learning successes. And so let's start talking a little bit about reinforcement learning. Reinforcement learning is both extremely complicated and extremely simple. On the complicated end, there have been huge teams of brilliant researchers working for years to develop the algorithms that we use today. And those algorithms are notoriously finicky. I remember using some and doing everything right and not having my runs converge. The system wouldn't even learn anything, even though I had it all set up correctly. Now, after years of iteration, we're getting much better at that. The algorithms that are used that gain popularity now are not necessarily always the very highest performing, but they prioritize things like ease of coding and reliability, the ability to run consistently. What you still need to know, though, if you're going to import one of these reinforcement learning libraries that's already prepackaged and just click go, is how reinforcement learning works in order to set it up correctly. Fortunately, that's the really simple part of reinforcement learning, because it's a lot like how humans learn. We observe our environment, we choose some sort of action, we get rewarded or punished for that, and we adapt our behavior. That's just what happens in reinforcement learning. On the computer side, we have a simulation. Sometimes we call it a gym, because that's where the training occurs. And that gym will take its state. It'll give us the variables that we observe. We pass to it the action that we choose. It gives us a reward or punishment, and then we iterate that. Now, just to make this a little bit more tangible, there's like the Hello World example called cart pole. Cart pole is just a cart on a rail moving in one direction. This is in a simulation. And what you're trying to do is move this cart to balance a pole on its end. Now, it's a pretty simple case. 4 things that count in one observation. You get to know the position and velocity of the cart. You get to know the position and velocity of the pole. There are only 2 actions that can exist. You can only move left or right along this rail. And the reward is simply you get a slight positive reward if the pole is still standing in each frame, or each second, however you want to divvy up time. And you get a punishment if the pole falls over. So that's what a simple reinforcement learning gym is. Okay. Now, after maybe a few minutes, 100,000 observations, it can be pretty good at that. But that's a very rudimentary example. So let's talk a little bit more about an advanced example. So on, let me get the date right, March 10th of 2016, in the 19th move of the second game, AlphaGo chose an erratic placement playing against the world champion. It was such a strange move that the commentators, who were expert Go players themselves, thought it might be an error. And AlphaGo thought that it was about a 1 in 10,000 chance of being chosen, that particular move. But it saw something that the humans didn't see. It ended up going on to win that game and relegate humanity to second tier in one of our most ancient and prized competitions. Now, this was certainly a breakthrough moment, but it was catalyzed many years earlier. On January 1st of 2013, DeepMind announced that they had used reinforcement learning to beat human experts in Atari games. Now, that led to a huge rush of research by big AI labs investing tons in reinforcement learning, and caught a lot of it, ultimately leading to this AlphaGo game. But over that period, in those same years, kind of sparked by this Atari deep learning example, DARPA also took note in the cybersecurity realm, and they spun up the DARPA Cyber Grand Challenge. And that went for some period of development, and ultimately the competition where the these computer systems hacked each other and defended themselves in a capture the flag that was hosted at DEF CON happened just a few months after the famous Go game. But the Cyber Grand Challenge used almost no artificial intelligence in the same sense as what we're talking about here. It was almost all hard-coded rules. Over this period, where everyone had been flocking to reinforcement learning, and there were these huge successes and tons of investment, cybersecurity seemed to be almost ignoring the field. And that went on for years after, until very recently. You can start to see it peaking up in the publication records. So what we have here is over a period of years, the last 20 years or so, what are the publications in cybersecurity and reinforcement learning combined. This was based largely on a repository held by Kim Hammer from ETH on GitHub. Kim, if you're watching this or here, thank you very much. Crystal then took that repository by Kim Hammer and built a machine learning classifier on that we were able to run through our corpus of academic literature that we maintain at CSET, and that was able to find 15% or more extra. But what you're seeing in general doesn't change so much. What we're seeing is that the number of publications in reinforcement learning for cybersecurity is relatively small. We're talking like 100 papers per year. So there's an opportunity to get on the ground floor here, but it's an exponential growth. And so that window might close. Okay, and kind of why this is happening, we think, or at least I'm not sure which is causing which, but coincident with this explosion is a build out of these cyber gyms. These are gyms like the Carpool example that I talked about as the Hello World, but for cybersecurity. A lot of these are coming out of the defense and intelligence sectors. The US has 2 on this list, one being Farland by NSA and MITRE, another one from Pacific Northwest National Labs. But several of our allies have done the same. They've got Cyborg from the Australians. We've got Cygil from the Canadians, Yawning Titan from the UK. Industry has played a role here too. There's one that's not on this list by Endgame, and Microsoft put out Cyber Battle Sim. Apple then took Cyber Battle Sim and have adapted it for their own purposes. Not all of these are public, of course, but several of them are open on GitHub. You can pull them right now. Notably Cyborg, Yawning Titan, and Cyber Battle Sim are out there. We'd like to take a little bit of time here to talk about Cyborg in particular, the Australians' offering, for a few reasons. One, it's fairly well maintained, and then 2, it's had a series of competitions, these called cage competitions over the last few years. You might be able to partake in yourself. I'd like to let Crystal walk us through some of those.
Yeah, thank you, Drew. So now I'm going to talk a little bit about one of these tools in particular that we introduced called Cyborg, and a little bit about how you could get started with it and how to use it and what capabilities it has. So the Cyborg tool is it stands for Cyber Operations Research Gym. This was created by an international cooperation research working group called CAGE, and they put out these different challenges, and so this is the topology for the CAGE 2 challenge. Since then, they've had another one that was about interconnected drones, and we expect them to have more challenges in the future as well. But for this particular challenge, you can see that there are a variety of hosts, enterprise servers, and the operational server, which you can see is the crown jewel that I drew very nicely. And this working group, their overall goal is to kind of facilitate the development of defensive cyber agents that can execute higher level strategies. So you see our defender that is put on the network there, and it's going to have a variety of actions that are available to it, which I will walk us through, such as restoring and removing systems, analyzing systems for indicators of compromise, deploying decoys, and these types of actions. And so the overall goal is to have a defender that is able to utilize a set of defensive tools and know which tools to use when to be able to execute some of these actions. And so I just want to set the expectations too. This is all very basic and abstracted away, but it kind of gives us an intuition for how we might start to develop some of these things. Yes, And so one other note about this challenge in particular and this topology is that in addition to our defensive blue agent here, there's also an adversarial agent that is trying to traverse the network, which I will talk about, and get to the ops server. And then we also have like a green team, which is simulated user behavior, so that it's not so easy to pick out the adversarial actions. It kind of creates background noise. So that is our setup for this. And so now I'll talk a little bit about the red team, if we want to think of it that way, or the adversary that is trying to gain a hold in our network. So this is just a basic rules-based agent. I want to emphasize that this is not using reinforcement learning for the adversary. And so it just is doing a series of actions with a certain probability of success. And those actions look like this. So first, the adversary will try to gain a foothold on the network by, you can imagine, like a phishing attempt. So it will compromise one of the users. And then it will try to discover remote systems. So this kind of represents like doing a ping sweep. And so it will take in a subnet and try to identify all of the other IP addresses that are on that subnet. Then it will try to discover network services. So this is like a port scan, and it will take in an IP address and tell you what ports are open and what services it has available. Then it will try to use an exploit that is available to it to create like a reverse shell, and then it will try to do privilege escalation from there until it eventually reaches the host that it wants to reach, and then it will try to impact and disrupt services. So that is the general kill chain that this adversarial agent is using, and it will kind of continue this network traversal until it gets to where it wants to go. One other note for this gym in particular, there are two different kinds of agents. The first one knows where the operational server is, and it's called the beeline agent, and it tries to reach it right away. The other one is called meander, and it doesn't know where the ops server is, and so it's just kind of picking around and choosing random targets until it finds its destination. So now I'm actually going to like demonstrate this gym real quick. So here we go. The first thing that I will do is I am going to initiate the environment. So there we go. So what I am doing here is I am importing in the agents that I want to use. So for this example, we are doing like adversarial agent and a very basic defensive agent. And I'm also importing all of the actions that I want to have available for these agents to take. Then I am saying initiate the simulation with a scenario file. So these scenario files are just YAML files that contain a mapping of systems to images. So it tells you how to initiate the different systems and like what parameters. So what OS, what kind of credentials, and things like this. And so now that we have it initiated, we can take a look at what information is available to our defensive agent. So as you know, I showed on the topology, the defender is part of the network, so it has full visibility into all of the systems. It can see the servers and the different hosts. And in like a real life example, you may not want to have a defensive agent that has all of your network information. And so you might think about this instead, since the network is so small, maybe this is like a subset of your network, or maybe this is like a portion that you want to train and develop an agent on. But it is also customizable. So you can choose how much visibility these different agents would have onto the network. And so it may not be that it has all of those user information. And so I will show you a little bit more in depth about what kind of information it has about the particular users. So for instance, if we look at user 0, which is just a regular user on the network, you can see that it has information about the processes, sessions. You know, we have OS information, and there we have some like credentials, password, and username. So this is kind of the information that it has for each system on the network, and what it has available to it. Another kind of piece of development or kind of open question around these gyms is how much information these agents need to be able to be successful and how much abstraction is okay. So we really don't have an answer to that question. This is kind of like the state of the art and how much information these agents use right now to be able to conduct decision making, but this is something to have more investigation on. And now I will show you what actions are available to the Defender right now. So what we are saying here is for the environment, I want to get the action space and just give me all of the actions that are available to Blue. So our defensive agent has a pretty basic set of actions available to it, which I hinted at earlier. So it can deploy decoys, it can monitor the network, which gives us a little bit of information, but not much. It can sleep, which does like nothing. And it can also restore and remove systems. And so you can think of it taking all of these actions as like using different defensive tools. And so to be able to use these different defensive tools, it also has parameters. So you have the actions and parameters. And I will show you a little bit more about how those interact with each other for the offensive agent. So let's take a look at our adversary and what actions it has available to it. So I will reset the environment now with the red team. And you can see that our adversarial agent, it can also sleep, do all of the actions that I described in that kill chain process. And it also has some specific exploits available to it. You can see here like Eternal Blue. And so to be able to execute any of these actions, it needs to use certain parameters. So right now, these are the parameters that we kind of have as variables for these actions for the offensive agent right now. Things like subnet, IP address, username, password, port. And these are all things they would need to be able to actually carry out any of the actions on the kill chain. And this is the information that it's trying to gain as it does its ping sweeps and port scans. And so I will show you a little bit more in depth now about one of these actions, which is the Discover Network Services. So what we are saying here is, let's look a little bit more at IPs and IP addresses. And so for our adversarial agent right now, it only has access to one IP. So this again is the situation where it has used a phishing attempt and it has gained access to like one host, one system on the network. And it can't see anything else yet. And so we might say, okay, I want to discover like what ports are open, what network services. And so if we tried to do that, but we tried to do this Discover Network Services with an IP that we do not know, so one of these ones that is false, and we try to execute that, you can see I get a false here. The action fails, basically. So what this is saying is that these agents are not really super representative of reality. If you have an adversary, they can, do a random sweep. They can find a random IP address to try to carry out some kind of action. But for this gym and these environments, everything is very concrete and moves through a certain system. So if we try to do this action again, but now we use a known IP, one of the ones that we have true, which we only have one for, you can see now we get some information. So now we have information about a local port and some more about the system. So this is kind of just to give you very basic intuition here. Now to develop the intuition a little bit more for how these work out, we are going to play a little game. So a little bit of audience participation would be appreciated. So this is like walking through one of the scenarios that I just described. So this is, again, we are the red team. We are on user 0. We have privileged access, but we have not scanned it. And now, can somebody tell me, given everything that I just said about this setup, which of these actions you would choose first for what you would want to do? Yeah, in the back. Action 1. So we're going to try to discover remote systems. The action was a success. Now we have some more systems that we can see, but not too much information about them. So does anyone want to choose another action? 2? Yep. Which one do we want to do here? Anyone have a favorite IP address? Maybe just this first one, 119? and we had a success. So now we have scanned this system, but we still don't have access. So someone want to pick another action? 3. We're going to try exploits. We want to do the one that we just scanned, yeah? And we got privileged access. So this is just like a fun keyboard agent to show you some intuition for how to walk through. But obviously, when we are doing this in real life, we want to actually train reinforcement learning agents to be able to do these tasks. So this is like a graph of some of the the mean reward for us training our reinforcement learning agents. And on the x-axis is kind of the amount of steps or iterations through the training, and on the y is the reward. So we mentioned before that these reinforcement learning agents learn through positive and negative rewards. And for the Cyborg Gym and cage challenges, you can't get a positive reward. You can only get negative because you get a little bit of a hit every time you do an action like restoring a system or removing a system. But this is a variable that can be changed and developed as well as people make these their own. But we trained quite a few reinforcement learning agents, and after many steps you can see they get better at doing their job and interfacing with what would be the adversarial agent and protecting the network. So yeah, that is just an overview of that. And now I will pass it back to Drew to talk a little bit about some of the directions for development and challenges that we face.
Great, thanks, Crystal. And so if we can develop these things, there are still challenges. For example, what do we even, oh sorry, this went too far. Do we skip one? All right, we'll go back to here. So there are still challenges. For example, what do we want these things to do? Certainly we want them to defend networks, but what does that mean? How do you define that in a reward function? Is it maybe a weighted sum of confidentiality, integrity, and availability? Oh, maybe. What are the weightings? And then even if you have that, are all of the endpoints is all of the information, do they all receive equal weightings? This is a difficult challenge. And so, sorry, I'm surprised that this slide didn't go. That's the one.
Yeah.
Okay. And so even if we can establish that, now let's say that we've built these things and they're effective, they need to be protected. And that means a couple of different things. They need to be protected at several different levels. On the one hand, if these agents are deployed out into vulnerable networks and vulnerable endpoints spread across large networks, you should expect that they might be stolen. And machine learning systems are notoriously vulnerable to being circumvented, especially by somebody who has access to a model to play with. Alternatively, you might keep these agents back in some remote server, and then you just continuously send the observations back to that server, and it sends the actions out forward. But in that case, you might be increasing your attack surface a little bit. Now, ultimately, the decision might not be made based on security. It might be the resources. For instance, you might not have enough local compute on the network to manage one of these models anyway, so it might not be deployed out. Or you might not have the bandwidth to send all of the observations continuously back to your remote server. So those might be considerations as well. But a different protection issue comes up because when you're training these agents, we haven't figured out yet if there's a way to train the defensive agents without also building a comparably capable offensive agent. Now, if you build those offensive agents, it puts you into a whole different set of constraints and set of issues. If you have to build an offensive agent that's similarly capable, then have you really advanced the state? Maybe, but if it's unclear, maybe it's not worth this huge investment to build them in the first place. Or perhaps maybe you can build the offensive agent with the defensive agent, delete the offensive agent, or maybe just protect it very well. But this leads to a whole other level of protection issues. Now, if we can build these defensive agents and they're worthwhile, we have major trust issues that we've brought up several times. Can we expect these agents to be able to do what they're being asked, can they do it in in an environment that's not exactly what they were trained in. These environments where we're going to place them are somewhat different from what they were trained in to begin with. We'll come back to that. Sorry. Lost here. These agents have large observation spaces and action spaces to deal with. Now, if you imagine one of these networks that Crystal just built out, and it's got 10 endpoints that each has 10 pieces of software with 10 configurations, that already gets you to 1,000 different things to observe at any given time. That results in needing very large networks, both to have the space to pull in all of this information and to think about it as you move. Now, the way that we've gone about that is to just have more and more parameters built out. In a case like AlphaGo, it has particular network designs already built out for this type of application, because you can imagine a Go board is a 19 by 19 square, and that square is kind of like pixels in an image. So they were able to use neural networks that were designed for image processing and leverage all of that progress. For cybersecurity, there's nothing like that yet. Cybersecurity agents that we've pulled down all use the most rudimentary type of neural network, just a fully connected network, where every node in this network is in one layer is connected to every node in the next layer. It's not the most efficient necessarily, but as we build larger and larger networks, each of those is a parameter, and each of those parameters then needs to be computed on. And this can get you to a large number of computations that can be expensive. GPT-4, for example, which is the engine behind ChatGPT now, was reportedly cost $100 million just to train. And that's just for adjusting the parameters. That's not for pulling the data. They just downloaded the data. For a system like what we're talking about, you would have to run these simulations to create the data that you're training it on, and that can actually be the dominant cost. But fortunately, we're not at a scale as anything like GPT-4. So what we're talking about here is we've got our Cage 2 winner. That's a description. But let's talk for a second about GPT-3. We don't know how many parameters are in GPT-4, but we do know how many are in GPT-3 from 2020. This is several years old now. Already it was 175 billion parameters. Now compare that to AlphaGo. That only had 8.2 million. It's a tiny fraction of what GPT-3 had. Dota 2 is another one of these big reinforcement learning models. This one was used to play video games, like an online video game. And it had 20 times more parameters at about 160 million. One possible reason for that is because it had a larger action space to deal with. Where AlphaGo has a 19 by 19 square, and in the beginning you could use any one of those possible spots for a move, gets you to 361 actions. Dota 2, depending on which characters you select, could have anywhere between 8,000 and 80,000 possible actions. Now, the two AlphaGo and Dota 2 had a similar number of observations to take in. They're both using image processing systems. Dota 2 taking the pixels of an image that a human would look at. AlphaGo taking the positions on a board. It doesn't have 361, it's got 17,000 because they use one board for black and one board for white, and then they use several boards into the past so that it has all of these many boards. But it gets to similar numbers here. But what I'd like to point out is that this Cage 2 winner, with its 36 actions and 62 observations and 6,000 parameters, is still much closer to the Hello World example of Cartpole than it is to AlphaGo, which was state-of-the-art in 2015, 2016, getting close to a decade ago. Okay, and so we already talked through most of this. What I wanted to leave here was the trust issues. So when we get to how do we authorize these agents to do what we're asking them to do, these levels of trust that might even exceed humans, we run into a similar problem with authorizing self-driving cars. And so there are levels of autonomy that we can consider. Maybe those are something like this. We can think about these levels of authorization on a two-axis, complexity of the action we're asking and the impact of errors on that action. And maybe in the low case, these are types of things that are maybe already automated, something like automated filters on a firewall. It's easy to envision and the impacts are potentially low. At the high case, these are things that might need extra levels of testing and management. Things like aspects of credential management or patch creation and deployment. And so where does that leave us now? That puts us in a place where next week you can go and download one of these gyms from GitHub, download one of these agents from GitHub and run it yourself. Over the next maybe few months, you could start adapting those agents and those gyms to match your own circumstances. Maybe write your own scenarios and see where that leads you. And then from there, I think that we can start pushing further to understand what are the limits of these autonomous cyber defense agents. Are we stuck at this carpole level, or can we get to AlphaGo and beyond? Now, before I leave, I'd like to say that I've been pretty skeptical about this area, and to some degree, maybe I still am. The cybersecurity is complex, and the state spaces and action spaces can be huge. It's so dynamic and uncertain, but there's been progress before. Particularly this quote from Remy Coulomb I'd like to point out. Remy Coulomb, in this year of 2014, had just built the world's best Go program, and he was the PhD advisor of the lead programmer for AlphaGo, which then, in the subsequent year, went on to beat the European champion, and the year following that, the world champion. So with that, we're open for some questions. We have a few minutes. Please.
Thank you for your presentation. I'm sorry. I have a couple questions. First of all, I would like to ask about what particular architecture of reinforcement learning agent is best for cybersecurity. Maybe it's online, offline, off policy or on policy, model based, without model, offline RL or online RL. What is best architecture for cybersecurity task?
Sure, and so all of the things you mentioned now are about the reinforcement learning algorithm. And what I was mentioning there, which I think is also very important, we can come to that, the types of architectures I was talking about here were the neural network itself. So the agent that's acting is a neural network, and you can pattern the connections in various ways to be more or less efficient. Like the language models now use a transformer where they piece themselves together, or the images that we talked about are like convolutional neural networks. That's all patterns of the neural network itself. And then which algorithms we choose for how to do the training is another type of question. What I was talking about there is like maybe PPO is a lot more efficient or is a lot more stable than AC3 as an example. And so
okay, PPO. I see. Other question, what do you think, what may be a best approach when we, in cybersecurity task, usually we have a sparse observation and also sparse action. Some attacks maybe happen one per year, but for reinforcement learning agent, when we use some learning process, we should do a lot of steps. Steps, observation, reward. Steps, observation, reward. What is the best approach for learn cybersecurity reinforcement learning agent in case when we have a sparse observation and sparse reward?
I think that's just maybe a general problem. Reinforcement learning gives me hope that you can create more cases is because you're gaming against yourself than just drawing from the real world. And so maybe we can do more discussion offline. There's a little line behind you I'd like to hear from.
Okay, finally I have last question. Generally speaking, reinforcement learning agent include not a lot neurons, yeah? Because for example, PPO model, it is very simple model. And if we want to include some knowledge about cybersecurity threats, attacks, and something like this, we will add neurons. But other hand, reinforcement learning is not stability neural networks as usual. What do you think? What we need to do for add some knowledge, but maybe it's other architecture for reinforcement learning, because I think PPO is not good approach for really complicated tasks such as cybersecurity. What do you think? Maybe model-based approach such as Dreamer model from DeepMind, or last reinforcement learning from OpenAI and DeepMind to more better for this task. Or maybe other approach when we have a lot of small agent based on PPO model, and after that, upon of this, we have some meta-learning model which use this knowledge from a lot of different small agent. What do you think? What better for cybersecurity task?
Yeah, so in the competition that I mentioned earlier, the winning teams had this kind of approach where they had a model that was basically a controller model and then different approaches that it took depending on how the adversary behaved in the network. So I think to that point, there could be a kind of structure that is multiple PPO agents. And I also think with the offline versus online debate, it depends. Being able to learn from human feedback or human examples could address some of the sparseness, maybe red teaming examples on your network, which we then use as training data, so it does not have to be, so it is trained like that for when it goes live. But all of these different approaches are under investigation right now, and all of those things that you mentioned came up in our literature review, and I cannot say for certain that any of them seemed strongly better than others. It seems very dependent on the network, the tasks, the reward, and the different goals, but I think that those are all really important considerations for more investigation too.
Thank you.
Yeah.
Hello, sorry. It's a nice presentation. Thank you for that. My question is for you is that when we are applying the reinforcement learning in cybersecurity, so the main concern is the reward, because in the reinforcement learning, someone has to verify that whether the action is correct or not. So in the cybersecurity case, we always have a policy that whether it is a good action or not. So how the reinforcement learning will work if we don't have, or we have a predefined policies?
So if I heard right, you're wondering, will reinforcement learning still work if the rewards are sometimes incorrect?
Yeah.
Yes, I think that as long as you're able to get above some threshold, I think you can still do learning even with some mixed in bad signals. But there's also a concern about, can people give bad signals on purpose in the wrong times, and does that create vulnerabilities that can then be exploited? But it doesn't have to be, you don't have to get a perfect reward every time. And this is kind of comes up now with human feedback, where human feedback for reinforcement learning is a big area right now. And in that case, they can't even define a number for this is the reward that you should get, or they just say this is better than that. And sometimes maybe people will disagree about which one they prefer, but you're still able to overall get you to a better place. So I don't think it has to be perfect, but I think that you should watch what kind of vulnerabilities that puts into your model that's eventually trained.
Okay, yeah. Thank you.
Thank you.
Hello, thank you for the presentation again. I think my question was very similar to what Vashi asked. So I was just wondering how the risk analysis was done basically with RL in CyberSec. So that was one of my questions. And the second question was, do you also intend to do a kind of constraint optimization on the reward functions that could yield RL compatibility with different training sets or something like that?
Okay, so for the risk analysis piece, I think that there needs to be a lot of development to this. We have some kind of frameworks, like we mentioned with autonomy, and so this is like a good starting point, but it's going to have to be like cybersecurity specific, and also like just going back to basics about your risk appetite for your organization and what things you want to introduce. And then for your second piece, can you like repeat it again? I kind of lost a little bit of your question there.
So yeah, so I was just thinking there are different test cases test scenarios in cybersec, right? So generic RL model to fit into all of them. For example, you mentioned that you would be selecting different training algorithms and all of that. So similarly, is there a way you are trying to change or put a constraint on the reward objective function that could yield a better result, like giving it a feeling like a single RL mechanism that could support various cybersecurity features or scenarios and things like that?
Yeah, so I think that the general like way that the reward function is set up right now is like something like adversarial actions that result in malware on the system bad, otherwise pretty good. So it's pretty simplistic right now. I think the things that you're talking about would definitely be like higher level, and especially if you had like multiple reward functions or different objectives that you are trying to meet that you then combine to one reward function. But then you would maybe apply some of those pieces that you're talking about there. But right now it's still like very simplistic.
Okay, so that's something like an ongoing research area.
Yeah.
We can come down.
Sorry.